So in this video, we're going to talk about my favorite concept in biology, which are energy-coupled reactions. And so in this, we're going to do it mostly in terms of molecular synthesis and decomposition, which are very important processes in organisms, right? What they're doing is they're taking either smaller molecules and building up larger molecules, or they're taking larger molecules and breaking them down into smaller molecules, right? And there's a lot of energy considerations going on here. So let's start with decomposition, right? So decomposition, breaking larger molecules up into smaller molecules, breaks bonds, and it is going to it breaks bonds and forms smaller bonds, right? And it's going to release energy, right? So it's an exergonic process, right? And I'll talk about Gibbs free energy in a second. So this is an exergonic process. It releases free energy, Gibbs free energy. And I don't believe in AP Bio I think they took this off the equation sheet, delta G equals delta H minus T delta S, right? Where this is the enthalpy, the temperature, and the change in entropy. They used to require you on AP Bio. I don't think on this exam they will. They used to require you to sometimes calculate this. They'll give you a delta H, a T, and a delta S, and they'll make you calculate the delta G, which is the change in Gibbs free energy, right? But I think right now you just need to qualitatively understand the idea of Gibbs free energy. What you have in this picture here, right, is so the larger molecules form smaller molecules at energy released. That's called an exergonic reaction, right? And we'll talk about exergonic and endergonic reactions in a minute. But in order for this to happen, right, where does this energy go? Well, what you're going to have is it's going to be coupled with the reaction of you have adenosine diphosphate and an inorganic phosphate, and it's going to basically take the energy from your exergonic reaction and form ATP. Right? ATP is the currency of your cell. That's what it uses to store energy. They are little bits of energy, right? In a mole of them, you have about 7.3 kilocalories of energy. And so, really, when you go through decomposition, larger molecules go to smaller molecules. That releases energy. That energy is picked up by this reaction. This is called a coupled reaction, right? In order to form ATP, you need energy to be released, right? And when energy is released, you don't want it just releasing out in your body, right? If you just released a bunch of energy in your body, it would heat up. You don't want too much going out as heat. Some will go out, some energy will go out to heat. Nothing is perfectly efficient. It's a consequence of the second law of thermodynamics, actually, that you're not going to have either of these processes be completely efficient. And we're going to talk about that inefficiency in just a second. But the important thing to know here is that they're coupled, that you have a reaction that releases energy, and it's an exergonic reaction is coupled with an endergonic reaction that absorbs that energy back up, right? So this is decomposition. It's also called ATP synthesis, right? And this might make you think of cell respiration, and indeed, cell respiration is a decomposition reaction in the sense that it takes glucose and breaks it up into carbon dioxide and water, right? And then it forms ATP. It takes ADP and PI and turns it into ATP. But it requires some ATP to start, right? And you can see that, we'll talk about that, I believe, in the next video, where you in glycolysis have to input some ATP in order to get some back. So synthesis, molecular synthesis, which you take smaller molecules and you build up larger molecules, this requires energy. That should make sense, right? Also note that these large reactions to large molecules to small molecules, that's called anabolic. I don't think you need to know the vocabulary, but I figured it's important to just put it out there. It might be mentioned on the AP. Smaller molecules to larger molecules, that's a catabolic reaction. It is endergonic, it absorbs energy. Again, you don't need to memorize this, but you should understand the general concept of energy coupling. Right? You don't need to memorize this diagram, you just need to know the overall idea of it. And where does it get this energy, right? You can't just say, we're building from small molecules to big molecules. We're just taking in energy, right? The energy has to come from somewhere. Energy cannot be created or destroyed. That's the first law of thermodynamics. What you're doing is you couple it with an exergonic reaction, a reaction that releases energy. You take ATP, right, and turn it back into ADP and PI. You break that bond. This is an exergonic reaction, the breaking up of ATP. It releases a lot of energy. That energy is absorbed by this reaction of taking smaller molecules to larger molecules using synthesis, which uses ATP. Now, these reactions don't just happen in your cell. They go through enzymes, right? And that's going to be our first idea of how do we regulate this process, right? Well, the best way to regulate this process is by regulating these enzymes, right? So let's regulate. Right? You can regulate these enzymes. You can use you can use inhibitors or activators that will turn these enzymes on or off, right? Which will allow these reactions to happen. So let's look at the energy diagrams for a second. We have exergonic and endergonic reactions, which I put under, right, our decomposition, our exergonic, and our endergonic reaction, the synthesis, right? And what's going to happen, right? Delta G is our change in the energy of the system. Here, it's less than 0. The products have less energy than the reactants, right? And here what you see is we're going from large molecules to small molecules. Large molecules will have a lot of energy. Small molecules don't have a lot of energy, right? So energy is going to be released. But you can see that it's going to require some energy to start it. That is called the activation energy. And that energy is going to end up being lost, right? This energy that you have to put in, you get it back, but it ends up being sort of lost, right? It's not used. This is the change in energy of the products. This energy here is lost to the environment as heat. So that's your inefficiency, right? Hopefully you can see. This is the amount of energy that's released from the top here to the bottom. This is all the energy that's released. But this is the only energy that's put back into the products, right? You put in energy, gets released, it's lost as heat. Hopefully that makes sense. So endergonic reactions, right? Similarly, you have a delta G that is bigger than 0. It's the change in free energy of the system. You start low energy, you go to high energy. You add a lot of energy, you end up actually having to overshoot it, right? And so, again, this energy is lost as heat, right? So there's going to be energy in these situations lost as heat. But how can we make these processes more efficient? The answer is have enzymes, right? And that's what these show. These show that this inefficiency, this activation energy, is going to be lower if you have an enzyme, right? For both endergonic and exergonic reactions. This shows you the dotted line with an enzyme, the solid line without an enzyme, right? And so, in the end, right, you want to have an enzyme. Enzymes are going to be good for the cell. So that is basically energy coupled reactions and molecular synthesis and decomposition. Again, the important things to remember: energy is conserved. You've got to have these coupled reactions. Enzymes, you have to have enzymes, and they can be regulated, right? And there is an activation energy. There's an inefficiency. So those are the 3 big things that you should take away from this video.